Usually when we talk about a mechanical failure, you kind of expect a loud, obvious crash. A machine just snaps in half, and you instantly know it's broken.
Right, it's visceral. But in the microscopic battleground of precision transmissions, failures are, well, they're practically invisible until it's way too late.
Welcome to this deep dive. Today, we are looking at some leaked R&D engineering notes focusing on mechanical vocabulary. Our mission is to decode exactly what happens when ultra-precise robotics basically tear themselves apart from the inside.
And it's fascinating because these terms sound like concepts from a sci-fi movie, but they're actually just everyday headaches for robotics engineers.
Exactly. So let's start with the dramatic stuff. Imagine a robotic arm swinging a really heavy payload, and someone just slams the emergency stop button.
Oh, that sudden stop means the load instantly blows past the system's torque limits. The internal gears violently they actually disengage and then re-engage in this event called ratcheting.
Ouch, this sounds awful for the machine.
It is. The transmission doesn't just suffer severe physical damage, it completely loses track of its physical positioning.
So if it's doing, delicate manufacturing, it suddenly forgets where its hands are. But, the machine doesn't always slip, right? Sometimes you get buckling failure.
Yeah, buckling failure. That happens to a thin-walled internal component called the flex spline. It's not the metal snapping or tearing, it's a sudden geometric collapse.
Which is kind of like standing on an empty soda can.
Yeah.
It perfectly supports your weight until it just abruptly folds and crushes in on itself.
That is a perfect analogy. It just gives out. And engineers spend a massive amount of time running finite element analysis, or FEA, simulating these loads digitally just to prevent that exact soda can effect.
So how do they balance the demand for this ultra-lightweight design against the terrifying risk of it just collapsing?
It is a really precarious balancing act. Shaving off even a microscopic fraction of a millimeter of wall thickness, just to save weight, can instantly trigger that buckling under normal rated loads.
Wow, just a fraction of a millimeter. But a machine doesn't even have to suffer a violent collapse to fail. The everyday movement creates this slower, invisible death. I think the notes called it fretting corrosion.
Yes, fretting corrosion. Inside these transmissions, you have parts constantly rubbing against each other with these intense microvibrations. That tiny relative movement causes the surface metal to oxidize.
And it turns into powdery debris, right? Which is like the microscopic chafing of poorly fitting hiking boots slowly causing a blister.
Exactly. And inside a pristine transmission, that powder completely ruins the accuracy.
Wait, if the problem is just parts vibrating and rubbing, couldn't engineers just, torque the bolts down tighter, just lock everything in place to stop the micro vibrations?
You would think so, but locking it down totally defeats the entire design. These systems literally have to bend and flex to transmit power. You can't stop the movement.
Oh, right, because it's a flex spline.
Exactly. So you have to fight the friction, instead using highly specialized surface coatings or high-pressure lubricants designed to mitigate that specific oxidation.
And because that flex spline is bending thousands of times a minute, the continuous flexing creates our next issue, which is tooth root cracking.
Yeah. The alternating bending stress basically gives birth to these fatigue microcracks right at the base of the gear teeth. And since you can't see them, engineers have to run regular ultrasonic inspections.
Because ultrasonic waves bounce differently off a microscopic void than they do off a solid piece of metal.
Right.
It exposes the crack before the tooth actually snaps off.
That's the exact mechanism, yeah. But doing ultrasonic testing requires taking the machine completely offline.
Which is expensive.
Very.
Yeah.
So to monitor the health while the system is actually running, engineers rely on acoustic signatures.
An acoustic signature,
Yeah.
meaning every machine produces a specific distribution of sound frequencies when it operates, right?
Right. And when a part starts wearing down, that acoustic signature shifts.
It's kind of like knowing your own car so well that a new clunking sound immediately tells you something is wrong under the hood.
Exactly like that. Monitoring systems are tracking these acoustic shifts for non-destructive testing. They can catch an anomaly, like a failing internal bearing, way before it cascades into those catastrophic ratcheting or buckling failures we talked about earlier.
That is wild. The next time your robotic vacuum spins up or your smart car shifts gears, think about the intense, invisible physical forces battling inside those transmissions.
Yeah, from the violent geometric collapse of buckling to the slow oxidation of fretting corrosion.
Right. The machines around you are constantly aging, flexing, and whispering clues about their health. Mastering this vocabulary gives you a backstage pass to all of that.
It really is all about knowing how to listen to them.
Which leaves us with a provocative thought to end on. If individual machines possess a unique acoustic signature that alerts us when they are sick, could the ambient combined hum of our entire cities eventually be monitored to predict massive infrastructure failures before they happen?
Oh, wow.
Are our bridges and buildings humming a warning to us right now, just waiting for us to tune in?